Now let us introduce another topic, which is Poisson brackets. Okay, Poisson brackets is a very important mathematical topic with a strong impact on the analytical or the classical mechanics. Okay, Poisson bracket is defined as follows. Suppose you are having a function f, which is a function in the degrees of freedom q and the momentum, canonical momentum p, and another function g. It's a function in the same variables. We define the Poisson bracket as follows: of Poisson bracket of fg is equal to partial f by partial q multiply partial g by partial p minus partial f by partial p partial g by partial q. So what is the benefit of this definition? This will be clear in the next few seconds. Okay, but let us before clarifying the benefit, let us emphasize an important property, is that qp is equal to 1. Simply because partial q by partial q is equal to 1, partial p by partial p, I'm substituting here f is equal to q and g is equal to p. You have here partial q1 pp1, and the qp means partial q by partial p is equal to 0. qq, as you could see also and as you could verify, will be equal to 0. Okay, and pp will be equal to 0. So what is the reason, or let us have a very minor motivation. Suppose that now we are trying to get f dot, or the total derivative of this function with respect to time. F here is a function in q and p and t. So to get the full derivative, you will use the chain rule, which is partial f by partial q multiply q dot plus partial f by partial p multiply p dot plus partial f by partial t. The first two here, remember now, if you could go back to Hamilton's equation. The first of Hamilton's equation was that q dot was equal to partial h by partial p, and p dot was negative partial h by partial q. This is the Poisson bracket of f with h. Okay, this is the very elegant result. It just tells you that if you trying to, for any quantity, you are trying to get the full derivative, it will be equal to the Poisson bracket with this quantity with the Hamiltonian plus partial f by partial t. Okay, fine. So we have defined now the Poisson bracket. Okay, later we will find strong analogy or some use for the Poisson bracket within quantum mechanics. Okay, now we will go to another topic, which is the canonical transformations. Okay, this is also a very important topic with many applications within the classical mechanics. So what about canonical transformations now? Canonical transformations are a kind of transformations. Okay, they are point transformations. So given, for example, an original variable q and p small, we define the transformed variables q capital and p capital. Okay, again, this is a point transformation and straightforward. However, for this transformation to be canonical, we need q dot to be equal to partial h dash by partial p capital, and p dot capital to be equal to partial h dash by partial q capital. So what's h dash? H dash is simply h, the original Hamiltonian. However, it is written now in terms of q capital and p capital, not in terms of q small and p small. So for many of you encountering this at the first time, you will speculate that any transformation written in this form will be canonical, which is incorrect. Again, why? Because for some cases this form will preserve Hamilton's equation. Okay, however, the same structure, and some transformation in this type will not preserve Hamilton's equation. Okay, so to emphasize, let us, for example, consider an example and using maxima to minimize the mathematical steps. Okay, in the next video.